Okay, so we have a test tomorrow. We were talking about that right before class. You don't have to have 3 exams in the final. The idea, though, is that if you don't do well on one exam, it's not life or death, essentially. So does that make sense a little bit? Let me just make sure that I'm doing the right one here. That's 324. Jordan, this is the 324 link, correct?
Sorry, what?
This is the 324 link, correct? Can you hear?
Yep.
Okay. Because usually there's a bunch more people, but there's only you. So, all right.
Yeah. Kind of weird.
I just want to make sure that I clicked on the right link because usually there's a bunch of people doing it remotely. But yeah, so we have a test tomorrow. It's going to go over, sort of the major topics we covered. So what are the major topics? Can you see my screen, Jordan? Sorry to keep picking.
Yeah. No, you're good. I can see your whiteboard.
Okay. So. Why won't you allow me to do background? I wish whiteboard would stay this way, but every time it has to go back to this. I just find it easier to look on a black screen than a white screen. Although sometimes when you export it, you have to be careful. The old version of whiteboard was much better than this version. So, okay. So we're covering, some unit stuff. So talk about units and conversion, essentially.
Will you upload everything you're writing to?
Yep. I usually do that. Hopefully.
Yeah, I just wanted to make
Yep. Yes, sir.
The note card, is it one side?
You can use both sides of your note card. Yep. So units and conversion. So what is a volt? What is an amp? What is a watt? Those were the major ones. We didn't really care. I mean, I think we did the ohms as well, but we don't really care about what a Henry is or what a farad is, because it's not a made up quantity, but it's not particularly useful. And the reason why we want to know volts, amps, watts, and ohms is it helps us when we're doing things and making sure, hey, this all works out. This all makes sense. That the voltage, we get a voltage when we multiply these things together, or we get a current when we get these things together. And then we expanded on coulombs. Yes, sir.
Okay.
Yes.
Would you be open to like a bigger cheat sheet, like maybe not front and back, maybe like a page, just the front?
I think that's good enough. I don't think you need more than that. Yeah. Because I would write the test differently as a result. So I'd rather just have you focus on doing the basic circuit analysis, because once people start bringing in bigger formula sheets, they just put everything on there and you're convinced that you understand it. But then you just say, okay, well, I'll put this problem on and just hope it's the same thing. And it makes it harder to write the test in a way that actually is assessing, do you learn this stuff? Yes, sir. I made the test, so it took me 10 to 15 minutes to do it. And that's not to say that I'm special. I just know the material pretty well, so I'm fairly comfortable with it. So the rule of thumb is it should take you about 3 times to do the test as it would take me. So I think it was 45 minutes or so, give or ballpark. But I say that with a grain of salt. You don't have to rush. If you want to take your time and go get a drink of water, by doing it during lab, that's the biggest thing you can relieve is the pressure on yourselves, because in your head, when you're taking a test, you just feel real pressure and stress and anxiety. And I was very lucky. It only happened to me one time when I just got out of in my head and I just couldn't do the test. So I did really poorly on it. But for the most part, you just have to go back and just catch yourself and breathe. And remember, you're just trying to show what you've learned. It's not what was taught, it's what learned, because what you take out of this class is hopefully stuff that will stick with you. So when you work in your professional careers, it'll be able to translate into more understanding, more learning, that type of stuff. So yes, sir.
You probably already answered this, but we have just as much time as we have in lab.
Yes. Yeah, I can't go longer than the normal lab period because everybody's expected to do the lab period, right? But you could have a 5 o'clock class. So I can't have people sticking past 5 because that gives people who perhaps don't have a class at 5 or a job or some other commitment, it gives them the same opportunity. So everybody, it has to be equitable. So that's why it's limited from 2 to 450. You can't even, like, I know some of my colleagues will say, well, I'll start the test early and you can show up early. Well, what if you have a class until 9:15? If you started it at 9, it's not fair for those folks that come early. So it's not a judgment thing. I just try to make it as equitable as possible.
Not agree out.
You should have plenty of time, but I'm just saying that don't get stressed out because I gave a test yesterday and most people were there for the entire time. And I was surprised. Most of the time when I write a test, most people are done within an hour to an hour and a half. Yesterday was an exception for some reason. Yeah. But different class, so. All right, so we have volts, amps, watts, ohms, coulombs, joules, and then the other one is seconds. Right? Those are the big units. And then everything else, if I said, okay, how much does it cost per kilowatt hour? You might use dollars, but kilowatt hour is really just a joules per second times 3,600 seconds, right? So you're paying for joules is what a kilowatt hour is. It's a certain number of joules. So being able to do those unit conversions is just a helpful thing to make sure you're getting reasonable results. That was kind of the introduction. Then we started moving into some basic circuit analysis, KVL, KCL, and primarily mesh and nodal analysis. So being able to do mesh and nodal analysis and understanding how to go forwards, backwards, that type of stuff, understanding the concept of what mesh is, what nodal is, how you have to deal with either independent or dependent sources. And then do you need a super node or a super mesh? And so knowing when to use a super node or a super mesh, and ultimately all the super node or the super mesh is, it's a tool for you to say, I just need something to give me the voltage or something to give me the current. I need something else to provide that information. That's all that super node does for you, is just say, oh, well, the current through this device has to be the same as the current into this location. So I can just use it that way. So it's a description, but it's really just allowing you to look at the circuit and say intuitively, yes, it has to be this value. Okay. You can use a voltage divider rule or current divider rule. So those are some techniques, essentially using KVL and KCL to come up with voltage divider and current divider. So those aren't anything fancy other than just applying KVL and KCL and coming up with a pretty efficient way to do that. And then we talked about doing superposition. And this one I'll expand on a little bit because it's a topic that you may or may not have covered in 111 or 112. John said he does cover it in 112, but I forgot to ask Jude if she covers it in 111. But the concept of superposition is really just to help you to do analysis in the future. So you've got an existing system or circuit, you've done a bunch of analysis on it. Now something has changed in the system. And a lot of times you can model that change as adding in a voltage source or adding in a current source. So we really don't use superposition much in this circuit analysis realm because it doesn't really help us all that much. It's just when we look at real world systems in the future, how do we analyze those particular systems? So that's the concept of superposition. So you replace all independent sources by their internal impedance. And then one at a time, find the quantity you want. Yes, sir.
Will you ask us questions in a way that we say, use this specific method to analyze?
Yes, I could ask you that. Yeah. So do it one at a time, and then at the end, add them all up. to get that final result. You need to make sure you add them algebraically so you get a correct result. Okay. If you have a dependent source in superposition, by the definition, right, you can't turn that independent source off. So you have to keep it into the circuit. So do your circuit analysis, including the dependent sources, but you have to keep it in on all different cases. So if you have 10 independent sources and 1 dependent source, you have to do 10 separate circuit analysis, but that dependent source has to stay in all 10 of those. Okay. And then dependent sources, the general rule is write one more equation. That's the hardest part about dependent sources, because you don't know what the value is. It's an unknown. So you have to introduce an additional equation to be able to solve for that driving element. If you have that and you write that equation as a function of something else you're trying to solve for, or other things you're trying to solve for, then it's just an additional equation. And then you just dump it into your matrices and make sure you understand, you know, this just will fall out. That's the other thing too, is be good at matrices. You don't have to do matrices, but I hope because we've been doing them enough in this class, you're starting to see the power of, you know what, it's so much more efficient to use matrices. All you have to do is set things up properly. So you just have to do that initial setup where all your unknowns are, all your knowns are on one side and all of the unknowns are on the other side. Okay, so knowns, unknowns, or vice versa, it doesn't matter. And then just write your matrices multiplying your unknowns by whatever values you have. And then you can just invert and multiply both sides and you got it. In matrices, you can't technically invert and multiply. You multiply by the inverse is what that's called. So that's, you don't invert multiply, it's multiplying by the inverse. And that's it. Everything will fall out. So using matrices, especially as EET students, upper class EET students in particular, you'll start to see where it really will, especially in the power systems class, we do that a lot. So just setting you up for in the future to be able to do things in more complicated, because in the real world, you have such complicated systems with tens of thousands of different pieces of equipment. It's just not manageable to write tens of thousands of different equations. But if you put it in a matrix and you just keep track of things, it's not that bad. Okay. So matrices, and then we had superposition matrices, and then we have Thevenin and Norton. So being able to find Thevenin or Norton, and that includes if you have a case where you can't actually solve for the impedance, because normally to solve for the Thevenin or Norton equivalent, you turn off all the sources and you're good to go, right? You just calculate what the impedance is, you do the series parallel combinations and you're done. But if you have a dependent source in there, you can't do that. You can't turn that off. There's no effective way of doing that. So that's when we said, put a test source. And usually it's either a 1 volt or a 1 amp. You pick 1 volt or 1 amp because the Thevenin equivalent says no matter what the load you apply to your Thevenin equivalent, you'll get valid results. So I should be able to put a 1 volt or 1 amp source and get exactly the same results, whether it's 1 volt, 10 volts, a million volts, 7.2, it doesn't matter. So picking one just makes your work easier because it's 1 volt or 1 amp divided by or multiplied by something. But that's only for dependent sources. Okay. So we have our Thevenin and Norton, and then that was pretty much all. Oh, sorry. Max power transfer. And again, max power transfer is not one that you'll typically have to worry about a lot of times, but it's useful when we do higher level analysis of systems. One of the things we talk about in the power systems class is you're trying to make the system as efficient and optimized as possible. So you'd like to move the maximum power through your transmission system. You can't actually, but you try to figure out what that is, and then you come down a little bit to have some margin. And so again, this is another tool, just like superposition, where you actually it makes your life easier in future classes. But superposition, Thevenin and Norton, max power transfer, if we would just do KVL and KCL, you could do everything you needed to do with just those. But those other formulas actually will make your life easier. Thevenin and Norton in particular will really make your life easier when you get into the senior level classes, when you're looking at, I've got to calculate, I'm building my senior project and I've got to do something and I've got to set this up. And so that's just that type of things that you really need to be able to understand and make your life a lot easier. So those are tools that we're giving you to make your future lives easier. Because in 111 or 312 now is technically the course. Did you ever use max power transfer in anything other than just an academic activity? How about superposition or Norton?
We did learn.
You did, but did you actually use it other than just, there's not a lot of practical applications, but I'm telling you for superposition, there's one in fault analysis that we actually will talk about in a month, essentially. Thevenin and Norton is the same thing. We've already done that with Y-bus and building Y-bus, right? Where we said, calculate the Norton equivalent. And so having that good, solid, fundamental understanding that helps you understanding some of those future things. And then the last topics, inductors and caps. So finding voltages, currents, power, and work. And so what we saw was being able to do, I have a capacitor, the current through a capacitor, CdV/dt, and the voltage across an inductor is L di dt. And by recognizing these two, we see that the current in a capacitor can instantaneously change, and the voltage drop across an inductor can also instantaneously change. But the opposite is not the case. So my voltage across my capacitor, 1 over C integral of IC dt, and my current in an inductor, IL, equals the integral 1 over L times VL dt. And so because we're integrating those, which is, again, looking for an area under a curve, you don't have an instantaneous change in area. You have a small little change, even if you have a big, discontinuous output, it's still because that area, area you're integrating under is infinitesimally small, you can't get these instantaneous changes. So that's why it allows us to simplify our work and say, all right, well, my inductor eventually will look like an open circuit or a short circuit. So VL of infinity equals 0, and IC of infinity equals 0. But both of those, and the concept of infinity means it's steady state, but it actually, you're not going to wait for infinity, but you can do initial conditions, you can calculate things. So if you had circuits with capacitors or inductors, you can model them as open circuits, short circuits, that type of stuff, just recognizing what is the initial condition. And this only works, you can see, if my voltage in my capacitor, if the capacitor is initially uncharged, then we develop that concept of V0 minus has to equal V0 plus, which has to equal 0. Same thing with the inductor. If there's no current initially flowing through the inductor, we can use this concept of initial conditions. So when you're looking at what's happening in your circuit, is something changing and is something going up or down or doing whatever, you can sort of start off, and all these values here just based on those equations.
That helped that one DC of infinity.
This is VL.
Okay.
Oh. And that's pretty much all that's going to be on the test.
I noticed last night that because the homework assignment closed, we can't see the PDF that went with it, the problems on it.
Yep.
Would you be able to add those somewhere else in Brightspace so that we can rework them as practice problems? I didn't copy them.
How about wrong class. Sorry about that. That was number 3, right? How about it's right here? Here's the first problem. I don't know where I would put it in bright space that'll actually make sense because the homework is all in that spot. So I could put it under content, but it might be a little out of place.
I just know that when the assignment closes, you can't see the problems anymore.
Right, so that's what I'm saying. So you can go back to the video.
Okay.
And look at them now, right? That's what one of the questions I was going to ask is, does anybody have any questions on the homework? Yes, sir.
Can we go find some difficulties with comfort?
Problem number 2 on homework number 3.
Yeah, problem number 2.
Okay. Anybody want to give us some ideas on how to start this problem? So if there's VC equals 0, because we'll assume that it's no value, right? VC of infinity is going to equal what? It's going to be whatever voltage the 22 ohm resistor is going to look like, correct? So the way that I would tackle this circuit is because I'm looking in the steady state power, which is another way to say that the capacitor is fully charged. I would redraw this, whoops, 1.2 volts, 40, 22. And now I'm going to go ahead and put this as my VC of infinity or VC of steady state. Now, how would you solve for the current? Or how would you solve for the power dissipation? Probably the easiest thing to do. You could do voltage divider rule, but maybe solving for the current through there. In steady state, I is going to be equal to 1.2 volts divided by 40 plus 22. 1.2 over 62 amps. And now once I have that, the power from the 40 ohm resistor is equal to I squared times 40. Anybody want to see those numbers?
I'm still gonna do voltage divider rule.
Well, I don't, do I?
Oh, no, you never mind.
Because VC of infinity equals I times 22. So the only reason why I did the current was because if I had to do voltage divider, I had to do 2 voltage dividers. I mean, I could do one because once I know one voltage divider, the other one is going to be 1.2 minus that. But I just, once I have the current, I can just go ahead and directly calculate those parameters.
Yeah.
So I thought it was more efficient.
Do you have any weird funky dependent source problem?
We can create one. Sure. But let's just make sure. Are there any other questions on homework number 3?
Well,
Number 4.
yeah, I couldn't tell whether you wanted AC or DC there because of the symbols were a little. I didn't.
What do you mean?
Well, just because it's a DC source, but then your letters are lowercase and AC, so I was just a little confused about what exactly.
Why does it matter? I don't actually tell you what VS is, right?
Never mind.
No, it's okay.
I think I was just confused about how you wanted it.
If it's AC or DC, it's irrelevant to this because the VS, you can just write that as VS. It could be a sine of omega t, or it could be 5 or whatever. So the way that I would do this one, just as a suggestion, oops, is I would redraw my circuit as a VS 20. I'm going to put my capacitor here, and then I'm going to also put in a voltage source that is 12 volts, because just before I walk up to the circuit and just after, this is the initial condition. So this is my initial value that I would do here. Okay. Then I'm going to go ahead and do my 10. And I'm going to show this as a current source, and you can put it up or down, it doesn't matter. This is 2 amps. And this is 8 millihenry. Okay. Do we want to write the mesh equation? So that'd be helpful. All right, so let's do this. And let's do that. So we're gonna have minus VS. We'll call this I1 and this I2. So minus VS plus 20 I1. What's the voltage drop across a 5 microfarad capacitor? No. It is plus to minus 12. So it has that initial condition. So it is plus to minus 12. What else? What is the voltage drop across a capacitor? I'm sorry? It's, yeah, but it doesn't matter. It's, you still have to integrate it, right? That equation is still the same. So it's plus 1/5 mics integral of I1 minus I2.
Okay, then I interpreted this, I just assumed that you meant that across that capacitor there would be a 12 volt. across
Yeah.
line. I didn't think that we.
That's initially, that's why this says 0.
Which is when I thought we were doing this analysis. I thought we were doing this at time 0.
Well, that's okay, as long as you said at t equals 0. But isn't this value changing over time? You just gave me the mesh equation for t equals 0, correct?
Yeah.
So that's the reason why, as long as you had said this, that's perfectly fine.
Okay.
That equals 0. How do we do this next one? The minus 12.
1/5 microfarad.
So that becomes minus, and I'm just gonna copy this down here. Right, what else? Yeah,
Also, that's not really copied down there. I2 minus I1.
well, because I put the minus sign here, it becomes I2 minus I1, right? So mathematically, that's still the same. Okay, now we're at a 2 amp supply, so what do we do there? How would we do that? So we know that VL equals L di dt. But don't we also have a current with it? So how do we treat that initial current? We have this 2 amp over here, right? So how would you model that? Any thoughts?
Doesn't matter if it goes in.
Well, you would want it going in the right, you mean the direction of the current?
No, if we're just gonna say volt, then we don't know the change in current. We don't, does the current value actually matter towards whatever voltage drop that in that?
It does, because it tries to maintain that current after the switch has changed. So it wants to maintain that current.
But does maintenance of current depend on value of current at a given time? It's gonna maintain it no matter what value that is.
No, because eventually its initial charge is going to change, right? I mean, its state of charge is going to change. So it's going to start at 2, but then eventually go to something else, depending on how the circuit is configured. So it doesn't stay at 2, it starts at 2.
Yeah, I know.
Oh, I thought you said it's going to maintain, which to me implies stays.
No, it'll try to.
Okay.
It'll try to maintain whatever current value it would have been at anyway. So Does it not? Why would it depend on what current is currently traveling to? It would only depend on how that current changes.
Right,
If we don't know,
right.
so do you not include the equation?
Well, what I would do is, what is the voltage across this element? I'm running out of space here. The easier way, I think, to tackle this problem is we know that this is 10. We know that this is 2 amps flowing through, and I'm just going to draw it this way. We're really running out of space. This is 8 millihenry. So we know that this is going to be plus to minus 20 volts initially. And what we need to do is this voltage here, this voltage has to match 12 volts, correct? So what is that initial voltage has to be? This is 12. This is plus to minus 20. So I can do plus to minus 12. Then I go plus to minus 20. And then I've got a voltage VL of my initial condition here. So what does this voltage need to be to make KVL work? I go minus to plus 12.
But I think we said there's also going to be a voltage drop across the path there on the other side. which is-
That's it. That's absolutely right. But we're just looking for the initial condition for the voltage here.
the initial condition that's going to be,
So we'll do minus 12 plus 20 plus VL of 0 equals 0. Get this out of the way. So VL of 0 equals minus 8. So the way that I would model that into this equation, and I shouldn't have put this over here. Let me get this out of the way. Should have done this in whiteboard. Is that is correct? This is I2 plus 10. But then what I would do is I would add in my initial condition of minus 8 volts. Actually, it's plus 8 volts, isn't it? Because it's a voltage drop in that direction, and that would equal 0. I forgot one thing. I still need the inductor, the 8 millihenry inductor. So what's the voltage drop across an inductor?
that'd be minus. Got minus 12 and plus 20.
Well, it's minus 8, so it's like this. It's going so it's going it goes plus.
I'm saying it would be minus in the equation.
Yeah, but it's a voltage rise, isn't it? The minus 8 means it's a voltage rise.
I mean,
No. What I'm saying is, if I do, let's go over to whiteboard so I actually have room. So my capacitor here, let's just say this is 12 volts. This we say is 20 volts. And this one we'll just show it this way as VL, correct? So we said VL equals minus 8 volts, correct? So this is actually going to look like this. Right?
yeah, which I agree.
So this is 8, 12, 20. So let's go to the KVL here. So we have minus 12 plus 20 plus 8. So yeah, so you're right. So that should be a negative number. Yep. So that should be, where am I? Over here. That should be minus 8. And then the last thing I need is the voltage drop across the inductor, LDIDT. So plus 8 milli times DI2 only dt, and that equals 0. So these equations, oops, are the two mesh equations, writing all the differential equations and including initial conditions. Hard, easy. There's a much easier way to do these, but we don't have the tool. That's Laplace transform, which you'd get maybe if you took differential equations. But because it's no longer required in this class, we have to present differential equation Laplace first. And so we have to do a little bit of math to show you where Laplace is. So we're basically covering what would be normally covered in Laplace, and we would just cover it here. We've kind of done it that way in the past, but I would have already presented differential equations, and so it would actually you would have seen it. So this is a differential equation, but we're not going to solve it. We're just going to leave it like this. That's why it's write the mesh equation. Okay. Any other questions on the homework? There was one question about this. Should be able to give me values here, right? Because you know L, and you know, because calculating the voltage drop, VL equals L di dt. I can calculate the slope here, and here, and here. So I can calculate di dt because it's y equals mx plus b. So I know how to calculate m, and I really only need m. So I know the slopes. So this one, the way I would tackle this problem is I would say from -3 to 1. My slope. So this is my time periods. I'd calculate my slope. So I have -3 to -1, or +1, I have 1 to 3, and I have 3 to 7. Those slopes you should be able to calculate. So then all you need to do is L times M, or di dt. Those are just slopes of the line. So this one wouldn't have been too bad, because you can tell what is the voltage drop. It's a constant. So I would have just drawn the curve. That's how I would have done this one. I would just drawn the curve. Okay. This one we went over. Any questions on this? All right. So you said you had a Thornton or Nevenin. See, I did that, Nevenin, Thornton. Sometimes I do that just to say it's all. And sometimes I actually screw it up. Do you want to look at one of the homework problems? Let's see. Do we have one here?
I'd rather a new one, just.
We can do a new one.
If there's anything that I haven't seen before, then it's just maybe another.
Sure. Let's look and see. This doesn't work. This is the book that I'm kind of using, and I probably will use this book next year because it has some pretty good stuff. So let's look at the exercises.
You know how many questions are on it?
5 or 6. I don't remember exactly. 5 or 6.
And it's gonna be a written. Or is it gonna be a, because I know that, some proposals for written prices.
Yeah, so my preference is to have it do written because I can give you partial credit. If you do multiple choice, it's you got it or you don't. So it's a binary system. So I like to see partial credit because it really gives me a sense of what you're understanding and what you're learning. So that is my personal preference, is to do it that way. I do teach another class, but it's more of a service class to all the different programs, like team teacher with David Dvorak. And that class is where we actually have, that one is you just, fill in, pick the right answer. Essentially, that's multiple choice. But that is really just a simple, you know it or you don't type class. Yes, sir.
I think the way John does it is he does multiple choice exam, and then for some of them you get points back if like a large sum of the class answered one answer wrong, or if you think that you should get multiple choice, or you should get part of one, you can show them the work that you did for that problem. And then you may or may not.
Yeah, and again, it's not a judgment call on him. It's just, I feel personally like I can really do an assessment to see if you understand it or you just pick the right answer. So that's just it's more work for me, but
Yeah.
I prefer it that way. But I mean, we can try. If you'd rather do multiple choice, we can try it. Okay. All right, pick a problem. This one doesn't have a dependent source. No dependent, no dependent. Oh, 39 looks a little bit easy. Want to do 40? Pardon? Trying to challenge me. We could do that. It's almost the same problem. It's just looking in a different direction, but that's fine. So let's do 41, which says, find Well, we want to do Thevenin and Norton, so we can just use this as a template. We don't care about the power dissipated. If we add a 1K ohm resistor or 4.7, once we have the Thevenin and Norton, it's fine. You want to do Norton, Thevenin, or both? Okay, which one do you want to start with? All right, so let's see. So we have-
This book, did you put the book in the syllabus?
No, because I just found this book that was close enough, so I had been looking all summer for a decent book based on the fact that we no longer have differential equations, and it's not ideal. They get into a lot of math up fronts, but it does have some pretty good circuit analysis, so I'm leaning this way. The book we had in the past was perfect, but it's more geared towards knowing differential equations up front, so that's why we had to shelve it. It's also a really old book, and so it's hard to get copies of it, but I think I'm probably going to recommend this book moving forward. So it's this book right here. It's Hate Engineering Circuit Analysis. You can see it over here,
Oh, yeah.
9th edition.
And what about-
You can take it, or hopefully it's being recorded.
Oh, okay.
Is it not being recorded?
No.
Let me just double check.
That's recording.
Oh, okay. You see the little thing clicking up and down?
Yeah, it's up in the light over the corner there.
Okay,
So I think it's been going since the beginning.
good. Sometimes I check, I forget. All right, so we're gonna do, we got a 10K ohm, a 1 volt, a 20K, and 2 times 10 to the 4th or 0.2 milli V1. So let's see, we have 10K. I'm just gonna go back and forth because obviously my memory is no good. 1 volt, 20K. This is V1. And then we have a current source, which is 0.2 times V1. 0.2 milli times V1. And we want to go ahead and calculate the Thevenin or the Norton in this particular case. So the question is, which one do you want to do first? You want to do Thevenin, Norton? Thevenin? All right, so what we need to do is we need to open circuit this particular element. So we're going to be looking for open circuit voltage between VA and B, that's V Thevenin. So what I'm suggesting is, I think it would be easy to write two nodal equations. And when we have V1, we essentially will know what the open circuit voltage is. Would you agree? So let's say we have that. So we'll do the V1 node. So we have V1 divided by 10K is the current through the 10K resistor. Plus, well, oh boy, we have to do a super node because we don't know the current through there. So we're just going to go ahead now because the current through here has to be essentially the sum of these currents if you got them correctly. So now we're going to just continue on and include the nodes. We're going to treat this as a short. So we have plus V2 over 20K plus 0.2 milli times V1. And there's no current into the node, right? No current into that particular node. Everything is out of the node. So all is well and good, but now I got to write another equation. V1 minus V2 is equal to 1 volt. So let's see, I've got 1, 2, 3 unknowns, but 1 and 2 equations. Yes, sir.
You B1 is, or sorry, BI equals B1 over.
Yep. Very good. So that'll give you our voltage. So now I just got to go ahead and put this into a nice form. So I'm going to go ahead and set up my matrix. Here's my first equation. It's set equal to 0. This is going to be equal to, and I'm going to go V1, V2, and then VI here, okay? So this becomes 1/10K, 1/20K, and 0.2 M. So now I can, and I just recommend this to keep track. Go ahead and write, well, write your matrix. So you've got the first equation. The second equation, I've got a 1 over here, and I have a 1, a -1, and a 0, because there's no multiple of VI. And then now I have to move everything to the same side, correct? So this is 0, and then I have 1 -1/10K. Oops, wrong spot. Sorry about that. 0 and -1/10K. And my V1, when I solve this, is going to be equal to my V Thevenin. Confusing?
I think I'm setting up matrices wrong, or I think I'm like combining matrices, like try and solve them. I can get them set up right, but then what equation with matrices?
Okay. Perfect. So does anybody else want to see how to do that? So I'll call this SRC matrix. I'll call this my Y matrix, and I will call this my V matrix. So what I'm going to do now is I'm going to bring up MATLAB, and I'm going to show you. Actually, let's rewrite this just so we have source equals Y times V. I want to solve for V. So V equals, and I got to get rid of the Y, which means I have to pre-multiply. So when you multiply matrices, you have to be really careful about dimensions. So it's Y inverse times SRC. So all I need to do now is enter in my matrices. Where is MATLAB?
I think I'm doing SRC.
I'm not sure why I have 10 versions open. Let me just clear out some MATLAB stuff. There we go. So SRC is equal to, this is just how I enter it in MATLAB. You don't have to enter it in this way, but I find it to be efficient. It's 0, 1, 0. So I have to use open brackets, 0, semicolon moves to the next row, semicolon moves to the next row. That's my SRC matrix. Now I got to use my Y matrix. Same concept. I use my open parentheses. So 1 divided by 10 E3. That's 10 to the third. 1 times 10 to the third. Now, comma, because I'm staying in the same row. 1 divided by 20 E3, comma. And then the last one is 0.2 times 0.2 e to the -3, right? Move to the next row. 1 - 1, 0. 1 - 1, 0. Move to the next row. 1, 0, and then -1/10K. 1, 0, -1 divided by 10 E3. Does that look about right? Entered incorrectly. So now I'm going to solve for my V matrix. And as I said in whiteboard, it's V equals Y inverse times my SRC. So V equals Y raised to the -1 times. And this shows that B is equal to 0. Is that right? Is that right? Right here. V1 equals V, and then when I pull this to the other side, oh, no, wait a minute, you're right. So this shouldn't be, no, what this should be is VI equals V1, right? Because, no, wait a minute, let's see. So VI,
You could get rid of it. but-
The
Then
thing
you
in
get
current.
current.
yeah, that's true, yeah.
that checks
So
out.
V1 equals VI, so this. This is a 1. So that's the nice thing about MATLAB. I screwed up and it's easy enough to say. You just change this to -1. I think that that's correct once I pull it over. And now I'm going to rerun it. That's what you get. And we said VI equals V1, so they should be the same. So it's 0.1429. That is the Thevenin equivalent voltage. To get the impedance, now I'm going to go ahead and put a test source on here. And you can put whatever you want. What I would suggest is I put a current source in here because I've already got all the nodal equations pretty much set up for me. So if I just put a current source in here, 1 amp, and it doesn't even matter the direction. This is 10K, 1 volt, 20K, and 0.2 V1. The only equation that changes is here. So now this is going to be equal to 1, right? That's the only modification I made was right here. So when I do that, what changes? This top row now becomes a 1. So to redo this, all I need to do is go back here, change this to a 1, and rerun my equation. Now I've got my voltages. They're all, so V1 is equal to 2.857. So V1 in the second case is equal to 2.8573. I've got my voltage. Wait a minute. Why am I struggling with this? I've got my let's just draw it over here because it's running out of, or actually I can zoom out a little bit. So this is my current, and then the voltage across this node is 2.85 whatever. So what I can do is I can replace this by this. So my R, Thevenin, or Norton for that matter, is going to be the same. It's 2.8573 K divided by 1 amp. So it's 2.8573 K. That's the reason why you just pick a 1 amp or 1 volt source. It just is equal to whatever that voltage calculates out to be.
But you know, the, short the voltage source, you know.
No, you can't short a dependent source, right? You can't replace it.
No, it's over.
You can't open it either. You can't replace a dependent source by its internal impedance. It has to be moved completely out of this. You have to keep it in the circuit. And to find the Norton, I don't know if you want to spend the time to do it because we only have about 20 minutes left. I would just put a short circuit across here. And I would probably I might even do the same thing because V1 is going to be equal to 0 at this point. So you might even just do nodal analysis again. Because your 10K resistor is completely shorted out. You're only left with 1 node. I might just go ahead and do that again. You can once you have this and this voltage here, yes, you can do a source transformation. Because a Norton and a Thevenin, you should be able to go back and forth because they're equivalent to each other.
Did you take the 2.8 multiplied by 10K?
Nope. No, what I did with my test source is I went over here. I just said this is a 1 amp source. Then I went ahead and calculated the voltage across here, this 10 volts. So if I know the voltage across this 1 amp source, then the circuit has to look like that much impedance because it's driving 1 amps through a box, essentially, right? So this is 1 amp and this voltage is 2,853 volts. Then I know that this has to be a 2,853 ohm resistor to get 1 amp flowing through it. Okay, I don't need to do any calculations. I just know that that's the voltage across that current source. So that's what the rest of the world has to look like to the current source. It has to look like that almost 3K ohm resistor. Okay. All right, what else? Yes, sir.
Could you run through how to set up the matrix if you were to have a solution problem with the dependence on?
Set up the matrix or set up the equations? Because the matrices, the
Well-
approach never changes.
The equation?
Yeah, let's take a look at an example here. Let's see, where is superposition? Seven. Here we go. So the superposition principle, that's 5.1 exercises. And we want one with dependent sources, is that correct? This one or this one? I think one of these was one of the homework problems, so we want to do 12? All right, let's see if I can get a little more clever. Okay. Here's our circuit and we're going to do superposition. So what we're going to do is turn off each thing one at a time. What do you want to turn off first? You want to turn off the current source or the voltage source? All right, so we'll turn off the current source, which means this is open circuited. We have a 2 ohm, a 1 ohm, 0.2 IX, 1, and 2 volts. Okay. The IX is the current that drives through here. So in this case, what I probably would do is I would do loop equations. 1 and I2, and maybe do it that way. But I'm done at least with I1 because I1 equals 0.2 IX, correct? And IX equals, let's see, is this going to work out for us? IX is going to be equal to 2 times I1. That's going to be impossible if I do it this way. Oh no, IX is going to be equal to I don't think this is going to work though, because this is a current source that's driven by here. So if I do this loop equation, I have I1 is equal to 0.2 IX. So IX can't be equal to negative I1. That's just impossible, isn't it? Even though I have that value that way. So this might be a case. This is the only time I've ever seen where you might not be able to use a mesh equation. Let's see. Maybe I can't use it because this is impossible, right? I can't, these two equations can't exist. I1 can't be 2 IX and I1 can't be negative IX. It's two different things. So that ain't gonna work unless it's 0 essentially. So maybe what we'll do then is we'll try nodal on this one. Actually, do we want to do nodal or do we want to do something easier? Let's do this. So this is 3 ohms, and this is the same current IX flowing through here. 0.2 IX. And 1. And 2 volts. So this one, it just might be better to go ahead and to figure out if there's a simpler way to do it. So I know the current. Let's see, this is plus to minus 2 volts over here. I know that. Is there an easy way? So I know that this is also 2 amps. So 3. 0.2 IX. Oop. This is 1, and I've got 2 amps going through here. And I've got 2 amps coming in this direction. So
The problem with this being here, so we never done speak between in the first place.
it probably would have been easier, but it should be something that we can tackle. I'm just trying to figure out a way. We know that this voltage here across here has to be 12 volts from here to here. The put,
Across the.
this right here has to be 12 volts. Because that's what this voltage source is connected to.
Okay.
So we know that this is going to be equal to. This has to be 12 volts. The question is,
Where do you need 12?
right here.
2 volts.
Oh, 2 volts. Thank you. So that's the question, which is if that's 2, then I've got 2 amps flowing through there. How can I solve the current? Got the voltage. I don't have any other way. Because I know this one might be a case where
What if you did a source transformation on the 2 volts and you turn that into a current source, and then you just did nodal at that central node?
say that again, I'm sorry.
If you did a source transformation, you turn the 2 volt source into the current source.
I can't do that because they're in parallel. If they're in series, I could do that, but if it's in parallel, I can't do that. Yeah, this one you might not be able to, or it actually might be that this is equal to. If IX is equal to 0. Because I can't get the current, like this current here has to be the sum of these two. Well, that would mean that I is equal to 0 here. So this one might not be able to be done with superposition. This might be, because I can't see of a clever way. If I did V1 and V2, I know V2 is 12.
Why do you know there are 2 amps on the right side?
Well, I know that this has 2 amps. I actually don't know that for a fact. I know that this has 2 amps through here.
Yes.
So I do know that,
But that doesn't.
but that, you're right, that doesn't necessarily mean that this is 2 amps because the current could be going in the other direction. So the problem is that I don't have a way of calculating what the current is out of that 2 volt source. So I don't think I can do, well, let's try it. Let's try, let me erase this and see if we can clean this up. Give me some more room. Let's try nodal analysis because mesh analysis didn't work for us. But it could be too that it is in fact equal to 0. I don't know, maybe mesh would work, but it didn't seem like it was going to work because of those equations. All right, let's try doing that again. This is 2, 1.2 ix, 1 and 2 volts. So let's call this V2 and we'll call this V1. We don't care about the voltage in between those two. So we'll say here, 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 and here. So V1 over 2 equals 0.2 ix. That's the first equation, right? Because that current here is the same as 0.2 ix. And then my next nodal equation, V2 has to be equal to 2 volts. So the only thing I need to do now is,
Oh, wait, that's gonna be 0, because if IX is coming out of that, and you've got a different, like, you've got 0.2 IX going out of that, you can't have 2 different values for IX. That's physically impossible.
right, that's what I'm saying. It might be that they have to be equal to 0 here. Yeah.
It can't be anything else
Let's just double check this. So VI over 2
for this one.
equals IX. So yeah, so the only way that this equation works, because IX has to be 0 here. So maybe mesh analysis would be okay. And we would get IX equal to 0.
I mean, if you do nodal analysis at V1 using purely IX terms, you can do that. You're gonna get plus IX minus 0.2 IX.
Right.
0, which is impossible
Unless IX is equal to 0, right? Yeah. So it might be that in the first case, IX is equal to 0 in the first case. So let's do the second case. Maybe that one's a little bit easier.
That's why you've got another weird equation you could match.
Yeah, but it was the same thing.
Less than 0.
Exactly. So maybe mesh did work out. I tried to convince myself that that wouldn't work. All right. So let's do this other case where we have our 2 amp here. Our 2 ohm. 1.2 ix. 1, and this is a short circuit, correct? So immediately what we see is this 1 ohm resistor is out of the picture. That's gone because it's shorted out, right? So no current's going to go through the 1 ohm resistor because it's shorted out. So now, V1, but V2 is equal to 0. So we only have one node that we have to calculate, right? Because V2 is equal to 0. So let's see, we have this current and this current. So current in equals 2. Whoop. What just happened? I think whiteboard just quit on me. I'm not sure why whiteboard just quit. Hopefully it didn't lose all that stuff. Sorry about that. I have no idea what happened. Okay, it still seems like it's there. So this one we said was erased. That doesn't exist. So we have 2 going in is going to be equal to V1 over 2 plus 0.2 ix. Now we have to write an equation for ix. V1 over 2. That's basically all ix is going to be equal to. So now we'll put this in standard form. So we have 2. This
It's so much easier.
no, well, you can. I'm going to always stick with matrices because if I get really good at it, then I don't need to substitute. So
over 2 equals IX. You can just write IX when you place it.
I know, but that's the thing. When you stay consistent, you always do the same thing. And you never have to worry about it. So, but yes, you can certainly do that. So I'm gonna say. And then 1. This is V1 and IX. And so in this case, you only have IX equal to just the one term. So that's how you do superposition for this one. Okay. We only have a couple minutes left. Any last minute questions? Everybody know the details of the test? I don't think I've only gotten one person who's going to take the test remotely. So if you want to take the test remotely, you got to let me know by noon tomorrow. And remotely is take it during class or lab period from 2 to 4:50, have a computer on. So that, and with a camera so that I can see your work, see your workspace, see your work area. Make sure you have a chance to scan, which is camera's fine, and upload your material. Upload your material and be good to go. Or we'll just go to lab. We can do, I'll just bring the hard copies and scratch paper. You have either your calculator or MATLAB. It's up to you. But you can't do both. You can only have one or the other. And that's including if you use your calculator on your phone. So you can't use your phone calculator and MATLAB. You just can use one or the other. You can listen to music if you want, don't care. Okay, any last minute questions? Feel prepped-ish? Still got a few hours, right? How about in TV land? Let's see about TV land. Hopefully. People are there in TV land. Can you hear or see us?
Yep.
I got worried I clicked the wrong link because nobody showed up, so. All right, well, there's no other questions. Have a wonderful day. Take care.
Thank you.